Hey, it's Masaki from Dianza Competitive Programming Club, and I'm going to be talking about algorithmic complexity. So let's start with an example. How do we check if a number n is a prime number or not? And a prime number is defined as a whole number greater than 1 that has only two factors, 1 and itself. So the first thing that you might think of is to find the number of factors of n, and if you find a factor of n, then you can say that it's not a prime number, and if n is greater than 1 and only has two factors, then n is a prime number. So let's say you check numbers from 2 to n minus 1. 1 is always going to be a factor of n itself is going to be a factor of n itself. So going to check every single number in between and see if modulo 0 it's equal to 0. So this might be an example of that in code. In the main function here, I just have a note the start, which is going to be the clock time, the system clock time at the start of the program. Run this and then check whether it's prime. I have a really large number here, 1,000,000,007, and then mark the end, and then print out end minus start. So it'll print out how much time took place in milliseconds, and so if you look at this code is prime, so I have a function here, and then I'm going to plug in the number 1,000,000,007. If n is less than or equal to 1, return false. If n is less than or equal to 3, return true. So these are the edge cases for prime numbers. And then for every number from 2 to n minus 1, then if n is divisible by that number I, return false. And then if you go through everything and you don't return false, then return true. So this might be an example of a linear complexity algorithm. You go from every number to n and check whether it's a divisible or not. So let me go ahead and run this. So I'm using FRE open, which just outputs this to a file. So I'm going to run. And it's taking a little bit of time, but we'll see that, yeah. So 1,000,000,007 is prime, and it took about half a second. Or 5 seconds, I mean. 5,000 milliseconds. There's 1,000 milliseconds in 1 second. So how can we make this faster? So if n has another factor which is not itself, the largest value that number can be is n over 2. And if so, let's say you think of the area of a rectangle to be equal to n. And so you have this rectangle, right? Hypothetical rectangle. And the smallest rectangle this can be is going to be 1 by n. And this is always when it's a prime case. But the next biggest one is going to be when you have 2 and n over 2. So the largest factor that can be, the largest number that can be a factor of n is going to be n over 2, right? So you can search up to n over 2, and that would divide the number of steps that you need to take by n over 2. And if n is not a factor of 2, if you try dividing by 2 and you have a remainder, it's an odd number, then you don't need to check every even number beyond that. So you can divide the total number of steps as well. So an example might be this file. So here I have the same thing. And then the third line here, if n mod 2 is equal to 0, so modulus 2, taking the remainder after dividing by 2. And if that's equal to 0, if it's divisible by 2, return false. And then now I have starting value 3 to n over 2, and then I'm incrementing I by plus equals 2. So I'm looking at half the number of half the numbers. So this should be about 4 times as fast. So let's try running this. So the first time took 5,200, so 5,000, let's just write it down, 5,200 milliseconds about, and then this one is like 1,400 milliseconds. So about 4 times as fast, what you would expect. So this is already significantly faster. But it's still pretty slow, right? So how can we make it a lot faster? The factors of n only go by pairs, which means there's always a pair a,b, such that a times b equals n. It can be proven that the minimum of a or b is less than or equal to square root of n. So let's think about this again. So when you have 2 and root n, the smaller one is going to be 2. So when you check 2, you're also checking n over 2. So the minimum of, let's say this is x and y, of x and y, where x times y is equal to n, is going to be maximizing that value. It's going to be square root of n. So it might take a little bit of thinking about, but if you think about the area, if you want to maximize, like minimize the amount of fencing or something, like minimize the circumference or something, might be one way to think about it. The largest number that you can get is going to be root n. The largest factor that you need to search up until, it's going to be root n. If you do anything smaller, then you'll get a larger number. It'll be paired up with a larger number. So the largest number that you need to check is going to be root n. And so we can do this and go for I is equal to 3, I times I is less than or equal to n. So in programming, you usually don't want to use floating point numbers if you can help it. Comparisons with floating point numbers, and if you like mess with floating point numbers a lot, it can start to create a little bit of error values and stuff like that. So if you can help it, you don't want to use decimal numbers. So that's why instead of doing square root of I is less than or equal to n, you might want to try something like I times I is less than or equal to n. So that things like that are things to think about. And then we're also doing the same optimization of dividing by 2 first and checking the remainder, and then you can increment by 2 every time. And if n mod I equals 0, return false. So the same thing except going all the way up to square root of n. So how fast is this? The thing is, it's a little bit too fast. So let's say I comment this out for a second and run. So the first one took 5,200, the second one took 1,400. This is taking 0 milliseconds, and that's it's not actually 0 milliseconds, but it can't really detect it. So let's just do the same thing, but 100 times. So I just have a for loop here and run it here. Okay, so it posted it 100 times, and then runtime 9 milliseconds. So 9 divided by 100 milliseconds. So yeah, that's yeah, very, very fast. So increasing the linear to the second optimization is significant, but it's only a constant factor. It's only going faster by like 4 times or something like that. That's a good amount, but if you can get faster in the time complexity wise, and a significant time complexity wise, you can make really, really huge gains. So we're going to be talking about time complexity in Big-0 notation next. Okay. So what is time complexity? And let's say you have a problem, right? And you don't need to look at this sample problem, but you have a random problem. And then on the problem, there's the problem ID, and then there's the time limit. And there's a memory limit that you usually don't have to worry about too much. This is Caddis, and that has like a difficulty rating and stuff like that as well. But important parts are going to be, one of the most important parts is the time limit. So time limits, most problems have like a 1 to 2 second time limit, and you can generally expect to do about 10 to the 8 operations per second. So if you look back at the example linear, you're doing around n operations, 1 billion, and then 1 billion divided by 10 to the 8 is like 10 seconds, or about 10. You'd expect it to be somewhere in the ballpark of 10 seconds, and that's a good upper estimate. This actually took 5 seconds, but so it's a good upper range estimate to pessimistic estimate maybe to think that it's around 10 to the 8 operations. And it's important to think about the time complexity of your program to make sure it will run in time. So how do you compute time complexity? How do you notate it? So there are like different ways to talk about it, and 3 of them are like big O notation, big omega notation, big theta notation. You don't really need to think about these too much. These are in the best case and the average cases, but for competitive programming purposes, you only need to think about worst case scenario, because you'll be thrown a bunch of different types of test cases, and you need to make sure that the worst case scenario, it's still gonna be working within the time limit. And if everything else works really, really quickly, but one case doesn't work or it's too slow, then it's not going to work for competitive programming. And so we want to look at big O notation. Big O notation is an estimate for big O notation is basically, if you increase, it might give you an estimate of how a running time for a program might increase if you increase some variable. So if we look at the first example with prime numbers, then so this first example might be big O of n, because you look at n different numbers and you're doing n different operations every time. And the second example is also looking at n numbers, but you're doing fewer numbers, so it's n divided by 4, but as we'll talk about later, you can simplify that down to order of n as well. And then the third example, this goes up to square root of n, so you're only doing square root of n operations. So if you increase the number to a large number like 1,000,000,007, you're still gonna be able to do it in square root of n time, and you'll be able to make estimates on how fast it'll run, or and things like that. So some common examples, let's say you have an array. So a vector is an array in C++, and let's say you find one index, you want to return the index of a certain index. The array, you want to take one index. So an array is generated like you have the starting location in the memory, and then you have the size of the array. So basically you're able to go to that location in constant time because you have one block of memory, one large block of memory, and then you have the start position. And so if I want to find the ith position or something like that, you just go to the start position plus I in the memory, and you can go directly to that memory address. So that's why you can find things in constant time. And yeah, so arrays allocate one block of memory, and you just go directly to that memory address because you know the starting part of that memory block. So it's very, very quick. Linear time complexity, let's say you have an array of random numbers and you want to check if there's a 0 within the array. So best case scenario, you might find a 0 at the very start and return true immediately. But worst case scenario, you go through the entire array, you check if it's a 0 or not, and you don't find any zeros, and you return false, right? That has to look at every single index of the array. So you would describe that as order of n. And so if you think about big O, big theta, stuff like that, big omega or whatever, the best case scenario, you might check one thing. and the average case, you might check half the things, but the worst case scenario, you're going to be looking at everything. And that's why you would describe it as big O of n. And it's called linear time complexity. You have to go through every single item. And let's say you increase the number of items in your array. Then it's going to scale linearly. If you think about a graph, the time it'll take to go through every single item is going to grow linearly with respect to in direct proportion to the size of the input data set. So that might be a linear time complexity thing. And then some other examples are like log of n, which you don't have to worry about too much, but if you increase by, if you keep on multiplying by 2 every time or something, then it might take logarithm of 2. A more common example for logarithmic time complexity is going to show up with binary search. So what happens in binary search is that, so you have a range of numbers. You have a range of numbers. You have a timeline. So let's say you have a number line, and you know that your number is between here and here, or you have you have an array of sorted numbers or something like that, and you define something. Well, you can check the middle and see if the number you're looking for is less than or greater than. And then if this is too big, then you can eliminate half of it, and then you check the half again, and you can keep on eliminating the range that you're searching with it within by half. And so you keep on dividing by 2 every time, and so that leads to logarithmic time complexity. To be more specific, log base 2 or something. So that's why this log appears, and it increases very, very slowly, even if you increase the number of items, for example, or the range. Even if you increase the range by significantly, it's not going to increase that much. It's very, very fast. So polynomial time complexity might occur when you're searching stuff. Let's say for I equals 0, let's say you have a grid, n by n grid, and then you want to compute the sum of a matrix with size n squared, and you want to sum up everything. So you have to go to every single thing, and when you increase the size of the square of the grid by +1, then you're going to be increasing it by n squared. So if you're at 5, then you need to check 25 locations. If n equals 6, you need to check 36 locations. So when you increase the numbers, it's going to increase very, very quickly, a lot quicker than linear time. Exponential time complexity might occur when you have to do something c times every time it's executed. So really popular example is the Fibonacci sequence, like 1, 1, 2, 3, 5, 8. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. So you keep on doing that. That's called the Fibonacci sequence. And then let's say you want to do a recursive function call, finding return Fibonacci of n-1 plus Fibonacci of n-2. So you have a random number, and you want to find this one. So this one is going to be Fibonacci of n-2 plus Fibonacci of n-1, something like that, and add these two together. But every time you call Fibonacci of 5, then it might call Fibonacci of 4 and 3, and then that'll call Fibonacci of 2 and 1, and that'll call Fibonacci of 1 and 0. And if you get 1 or 0, it'll return n itself. So every time you call it, it's gonna increase by 2 to the n. In this case, you have 2 options that it splits into every time, and you have to calculate quite a lot. So there are a lot of optimizations to this, and with it, and it serves as an introduction to like dynamic programming and things like that later. But this can be an example of kind of exponential growth. So what are some properties of big O notation? You have to get rid of constant factors. So let's say it takes 5n time, order of 5n time. You'd simplify that down to n, O of n. So if you remember the first thing, this was order of n time, and then this was order of n over 4 time. The second version was n over 4 time. But you'd get rid of the constant factors, like 1/4 is a constant factor, and then simplify that to order of n. So the first two examples are both linear time examples for finding whether or not a number is prime. And then simplify everything besides the dominant term. So you might have seen this in algebra or calculus or something. If you think about the limit as n approaches a really large number, the other factors become a lot slower. If you think about like 5n plus 12, let's say n is a billion. A billion plus 12 and a billion is not very different, right? So you can get rid of the 12. Well, what about you do the same thing with n squared? Like n squared, let's say n is 100 or something. So 100 is 10 to the 2, and then n squared is like 10 to the 4, and then 100 in comparison to 10 to the 4, or like 10,000 or something, it's just not that big. And as you increase bigger and bigger, then it matters less and less. So that's why we'd simplify down everything besides the dominant term and call it n squared. Because this is going to be the limiting factor. N squared is going to be the limiting factor in terms of whether you're going to get everything done in time. And then if you have terms multiplied together, then that is going to be significant. So if you're doing a log n operation n times, then you'd say it's n log n time or something like that. So you can't just cut away some factors. You can combine terms if they multiply with each other. And then, so there's faster time complexities and slower time complexities. We talked about log of n, order of n, constant time, like you're searching in an array or something, and then there's like n log n. And then there's polynomial time complexity, and there's exponential time complexity, and there might be factorial time complexity. So these become very, very slow. But that doesn't mean they're unusable. It just means that they're very slow. If you have small n values, you can still have solutions that use n squared, order of n squared solutions. You can still use n factorial solutions. If the limits of the problem allow it, you can just solve the problem with a slower time complexity, and making a problem run faster than required, it's not necessary at all. And if you can solve something slower and you can solve something faster, you don't get anything extra for solving it faster for the most part. And another thing to watch out for is that big O is not necessarily a running time estimation. So let's say you can solve a question in order of n time, or maybe m squared time, using different variables, using different parts of the question. You can't really say that order of n time is better than m squared in a vacuum. You can't tell without knowing the ranges of n and the ranges of m. So like linear isn't always better than quadratic time. It just depends on how large the variables go to and things like that. So to get a better estimate of the number of operations you'll be doing, you should try plugging in real values. So for example here, we had 1 billion, a billion, and then linear time. So 1 billion divided by 10 to the 8th, 10 to the 9 divided by 10 to the 8 is around 10. So an upper range estimate might be like 10 seconds or something. So you can do something like that. Linear time, so 1 billion divided by, in linear time, divide that. For every second, you can do maybe around 10 to the 8 operations, so 10 seconds again. like the previous one, but you're doing maybe 1/4 the number of operations. So 10 seconds divided by 4, that might be somewhat of a rough estimate or something of the time, and that might be a good upper range. If you take root, then root of 1 billion, 1 billion, square root of 1 billion, or 10 to the 9, so 4.5-ish, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's around maybe 31,600, so 32,000 something. So if you think about 10 to the 8 operations per second, then that 30,000 or whatever, it's gonna go by really, really quickly, very, very fast, and you can see the results and the numbers that you see. So you can kind of predict that by plugging in some real numbers. And then this, you don't have to memorize anything, just like some random values. If you take like 10 to the 8 and divide it out or do some algebra, you can, or plug in some real values, you can figure out whether or not it'll run in time, and these might be some rough estimates as to how big of a number you can use for every time of time complexity and things like that. So you should try to think about that when you're solving problems. Another type of time complexity you'll see really often is n log n time, and this is found when you sort. It's most commonly seen when you need to sort an array or a list of items or something. So in Java, you might use collections.sort. In C++, you might use sort, standard sort from the standard library, and that's going to take n log n time. And these use a variation of quicksort and things like that. You can look that up, and you'll learn about it in CIS 22C. But you can generally expect to be able to sort things using comparison sorting algorithms and n log n time. And something else. So let's say you have 3 loops and you're doing one thing here. So this might be n times, and then this is n times, and this is n times. So this might be n cubed time complexity. So this problem, you're inputting a, b, c, and x, and then this is dependent on a and b and c. So you might also describe it as order of a times b times c, and so you might say it's order of a times b times c as well. And a lot of the times you can kind of simplify it down to 2 loops instead. So if you, sometimes you can kind of optimize further than that. So sometimes the requirements will require you to do something else. For example, in this, n is equal to 2,000. So 2,000 times 2,000 times 2,000, I think, doesn't really work. So you have to optimize a little bit. So 2 to the n, sorry. 2 to the n, you might include or exclude all numbers in a set. So pick any combinations of numbers, generate combinations, things like that. You can do in several different ways. You can use something like depth first search, something based on depth first search. You can do something with bit manipulation, things like that. But you can generate every combination of true or false for n numbers, then that might take 2 to the n time. In factorial, if you try every permutation of like a list of numbers or something, that's going to take n factorial time for n different numbers. So let's say you have 1, 2, and 3, and you want every variation of like 1, 3, 2, 2, 1, 3, then that's going to take n factorial time. You can either use a built-in function like next permutation in C++, or you can do depth first search, do something like depth first search and generate these patterns, and it'll still take n factorial time, but we'll learn about that in a future presentation. But for now, if you can start thinking about, well, how long will my program take? If I have 2 loops, then this goes up to n, this goes up to n. So I'm doing this thing n times, and then I'm doing all of that times n times, and you end up with n squared or something. Or I'm grabbing something, I'm doing one thing that's going to take constant time. I'm going to do something n times, it's going to take O of n time. If you can start thinking about that, and that'll let you start to analyze your time complexity, analyze, maybe predict how long it'll take to run your program, things like that. And so in the first example, you can kind of start to make estimates of how long something might take, and kind of predict that, and also not be surprised when you end up with time limit exceeded, stuff like that. So, and that's going to be it for algorithmic time complexity.